So let's have a look at a couple of these problems that are coming due. There we go. Okay, the first one is two parts. So let's start on the second part of this one, okay? So this is number 241. I put this part down on the bottom here, but let's start with this one. So what we want to do is figure out how to get from that diagram, from the picture to the diagram. All right, so what we have going on there is we've got a couple beams. We're assuming the beams have no weight. We're just going to look at that concrete slab, you call it, which is just a flat piece of concrete. And then we put some sand on there in a triangular pattern. And we want to kind of verify that we can go from this picture to that diagram. All right. Now, what's happening here is we've got a trapezoidal load, right? So we've got something going on like that. Now, if you look at how those materials are configured there, how they're put together, what I can see there is I've got a diagram like that. Now, if you look at the shapes of those materials, what the concrete is just has a constant width. So I think that's going to get us a constant load. And then the sand kind of starts at 0 and angles up from there. So I think that's going to get us a triangular load. So what we're going to do is take that diagram and kind of split it into two pieces. The sand will be on the top. That's the triangle because of the shape of the sand. And then the concrete's on the bottom. So the concrete is the rectangular bit, and the sand is the stuff on the top. And when you put them together, you get that trapezoidal load that you see. So any questions on that? What we're looking at? Yes, it is. Oh, 241. 241, sorry. So this is 241. So we good with that? 241? Yeah.
I'm wondering what the 2 meters is measuring.
The 2 meters is measuring center of beam to center of beam. So that's what we call the center to center dimension. And, you know, I was a little pressed for space, so maybe it'd be a good idea to look at this. What we have here, if you look at it kind of this way, if you're looking at it that way, is you've got beams, kind of like, you know, under your floor. If you ever crawl around in your crawl space, you've got what are called joists. Those are beams that hold up your floor. They have a certain spacing on them. Now, as it turns out, the spacing on those beams, which would be 2 meters, is
Pascal? Is that Newton meter cube? That's our pressure?
No, that's it's a kind of a density, but not really, because density is based on mass. It's a specific weight is the term for it. Yeah, we don't use mass so much in this class. All right, so the assumption you would make here is if you got 2 meters spacing on the beams, what that means is each beam then will support 2 meters of whatever's above it, okay? So if you can use the beam spacing to get the amount of the object above that the beam supports, even though they're not the same 2 meters, that still holds. Because this would go 1 meter over to get to the midpoint here, so that would be 1 meter for each beam, and plus you've got 1 meter the other side too. So the meaning of that 2 meters, even though it's from the center of beam to center of beam, is that it supports 2 meters of concrete and 2 meters of sand up above. Okay. So what we want to do then is figure out how much, what the distributed load is associated with those things. So the concrete there, if you look at that, the unit weight of that, or specific weight they call it sometimes, is 24 kilonewtons per cubic meter. Okay. Now what's happening there is that's 0.625 meters thick, and it's 2 meters wide. So if I multiply that by those dimensions, what I'm going to get is the amount of weight per unit length. And when you multiply,
It's not 4 meters wide.
Would it be 4 by 6? Do we want the height or the width or the length?
Okay, what we want is the height, which is 0.625, and we want the width for one beam, because we're finding the load per beam is what we're doing.
Beam, okay.
There are
So
two
we don't care about
beams.
the long wise, we care about the.
Well, and what we're going to find then is a load per meter along the beam. Okay, so when we multiply these dimensions together, if you do dimensional analysis, of course, you're going to see that the number is 30, and then the units are kilonewtons per meter. So that's telling you for every meter length of beam, you've got 30 kilonewtons that build up. So for 2 meters, you'd have 60 kilonewtons. For 3 meters, you'd have 90. For 4 meters, you'd have 120, et cetera, okay? So that's where this number here comes from, the 30 kilonewtons per meter, because what that is the height of the concrete, okay? Or excuse me, the weight of the concrete per unit length. So that's 30 kilonewtons per meter, as is this, because that's a slab of constant thickness, 0.625 meters, okay? So we good with that? That's like a load per unit length. Every extra meter of length of beam, you accumulate 30 kilonewtons more of weight, of load, as we call it. We good? I'm doing part 2 right now. Let's start with where this diagram comes from in the first place, because we're going from the picture with the beams that are 2 meters on center, and then we're moving from there down to this rather more simple diagram. Okay. Yes.
So 30 kilonewtons per meter is just the concrete or sand?
Just the concrete, because all I accounted for with that little line of calcs was the concrete.
Is that little 78 kilonewtons per meter, that's the sand?
Well, okay, the 78 is in part caused by the sand, but what would the number be for the sand if the total vertex height up here is 78? What would this number be for the sand?
78 minus the 30.
Yeah, it'd be 48, okay? So that's,
The sand the same way, but.
all right, so that's how the sand's going to add up. Now the sand is going to start at 0, which is why that's right down there at 30, see? Because
Sand area divided by 2, because it's a triangle, right?
it would be the same sort of calculation that I just ran. You know, I don't know if I divided, oh, well,
You do the
no,
width times the height, but divided by 2, because it's a triangle, right?
I would do that on the second step. I'm not going to do it on the first one, because what I want to get is these loads are somewhat instantaneous. So what I would do next would be to find what is the load per unit length of the sand at that point, and then you can assume there's a linear distribution as you work your way up. So you're going to run a very similar set of calcs like what I just did for the concrete, but you'll do it for the sand, and you're going to find it at an instantaneous sort of number right there. Your check on that is when you run those numbers, they should come out to be 48 kilonewtons per meter for the sand. And these are somewhat instantaneous readings as you work your way across, okay? So you'll use the height of the sand on the far right to calculate what will turn out to be 48 kilonewtons per meter there, okay? So as I've mentioned, you know, in the statics book, you get this picture right there. They'll give you that, and you start working with it. I want to just back it up a step and show you when you're working and you have to deal with this stuff, how you get to the picture. That's what I'm attempting to do here. How you break down a real life 3D situation to a 2D diagram that you can then analyze. That's what I'm trying to show you. Okay. And it's, you know, it's fairly involved, I guess, a little bit, but all the same, it's not, you know, really complex calcs. So it's just basic algebra, or not even that, just basic arithmetic. But you kind of have to understand where the pieces are coming from. That's the complex part of this, is kind of understanding what we're doing. Okay. So what I did was the concrete. What I'll let you do is the sand, and you're going to do a very similar set of calculations. And what you're going to come up with when you do it is you're going to come up with 48 kilonewtons per meter after you run it. That's the instantaneous load right at the right-hand side of the sand. And then being as how that sand is sloped, that should be a linear relationship here. This should be a straight line running across. Y'all okay with that? We got any questions on that? Okay. And, you know, we did this in class, and we did that dam with the door that was hinged and open. We kind of broke down the unit weight of water to break down to the pressure and then down to the load per length, the instantaneous load per length. I've done this with soil loads on a dam once too. I've done this in different situations. You kind of work your way through. If you've got a roof on like this building here, you're going to look at the weight of that slab up above and how much of it you would assign to each beam, and that's how you'll come up with the load on the beam. You might also have a snow load and things like that you might add into the weight of the concrete. You might look at some of these other things, snow and wind and things like that. Okay. So we're good with that? Questions? Okay. All right. Okay. All right, now let's look at the step after that, which actually I put on the top because that's really the more standard statics type problem is on the top there, okay? Where you find the resultant, okay? Now here's where you start doing the half for the triangular area and all that. What you're going to do is you're going to take that shape and you're going to break it up into pieces because you want to find an area, which would be the load, and then you want to put that area at a centroid. So you need pieces for which you can find centroids. And I can find the centroid of a triangle and I can find the centroid of a rectangle. I'll struggle a little bit more to find the centroid of a trapezoid. There is a formula for it, of course, but it's a little bit involved. So I find it just as easy to take a trapezoid as you see there and cut it up into pieces with a triangle and a rectangle. All right, so what I'm going to do is cut that across. And just as I was showing you earlier, the derivation of this gets us to, kind of where we're at here. I've got the concrete below the line and the sand above the line. So one thing I would point out to you here is that lower piece is 30. There's a common error that people make because it's just sometimes you get something right in front of you and you kind of grab it, right? And you see that 78. And sometimes people want to apply the 78 to the triangle, but that's not the number to put on the triangle because you've already got 30 for that rectangle underneath. That'll be 48, okay? So remember to take 78 minus 30 to get that height of the triangle. So what you're going to do then is find the areas of these shapes and then apply those areas, which are forces, at the centroids of the shape. So we got two centroids here, one for the rectangle, one for the triangle. All right, so you want to find the area of each. So the force, I'll put that as F for the rectangle, will be what? Just 30 kilonewtons per meter. And I like to track units through these because they do work out. And then I would multiply that by the 6 meters. And that would get me 180 kilonewtons. Okay, and that is the force right there at the centroid of the rectangle. Now, the centroid of the rectangle is 3 meters from A, right? Because that's a rectangle with a base of 6 meters. So you're going to want to dimension that over at 3 meters. Now, we've also got a right triangle, and that is not 3 meters to its centroid, right? Because a triangle, it's a third of the distance from the right angle, 2/3 of the distance from the vertex. Okay, we're going to measure this stuff about A. So what you're going to want to do then is find the force for the triangle, and that'll just be the area of the triangle there, and that should come out in kilonewtons, thousands of newtons, and that's 144 kilonewtons. And then you can use that, figure out that distance there. Nothing much to figure out there. Pretty simple little calculation to get that. Okay. So the thing on this is to break this stuff down. That's what you want to do. We kind of take it and break it into simpler pieces that we can handle more readily. So I'm going to take that distributed load and turn it into that. 180 kilonewtons in the middle and 144 kilonewtons a little bit off to the right there. And once I have that, then I can run through the numbers. I go sum of Fy, and that's minus 180 minus 144, okay, and that'll get you the total. And then I'll go sum of moments about A, and what I'll get out of that will be negative 180 kilonewtons times that moment arm of 3 meters. And I'm going to have another moment there to do, and what that's going to tally up to is minus 1,116 kilonewton meters, because that's a moment. And then also I ask you for a location. Okay, so what we're going to have for that resultant when you're done is you're going to have two ways to express it. The first way is just with these numbers here. The other way, though, is to say it's 324 kilonewtons down, and then we're going to go that distance over where we can put that load. And where we can put that load to cause the moment is at 3.44 meters over. That would be the solution on that.
How about the radius, if we have the 3 meters for the, we need to find the center of the
right triangle there.
right triangle?
Yeah.
We have a little formula for the center of right triangle.
I think you do, yeah, I think on the formula sheet it's there.
Where does the 3.44 meters come from?
The 3.44 comes from the fact that if you want a distance, the relationship there is that the moment is the force times the distance. So if you want the distance, you take the moment over the force. It's how far over you would put the force to cause the moment. Okay. So we good with that? We got any questions on that? So that's the run through that. That's a resultant problem with distributed loads. Okay. We good? All right, so that's force, yeah, okay. So we're good? Okay. All right, now we got another one too that's doesn't have the first part of this, but it does the part where you find the resultant is a little bit more complicated. It's got more pieces to it. Okay, so let's see. So that first one was on page 11A. It's right on there when you do it, okay? Okay, the second one's like that, and this one has a few little things going on with it. So this is on page 11B is where this is. And this is 242, I think. Yeah. 242, thanks. All right. All right, now the deal with this is you've got to break it up into pieces. And you've got another little complication with this, because what you're going to do is you're going to break this thing up into pieces like that. So you're going to have 3 of them. They're going to look like that. So each one of those will have a force applied. So we'll have a force on the right triangle, we'll have a force on the rectangle, and we'll have another force on the rectangle. Now, there's another little complication on this, and that is that you're going to get distances. Probably the most logical place to accumulate them is about that very heavy line that I just drew. So you're going to have distances from there. So you're going to probably calculate that distance and that distance and that distance, okay? Because that's where the figures, that's the boundary of the figures, where you change from the figures to the left to the figures on the right. And that's the line between them. However, where you want to take moments about is point A. So you're going to have to apply this 0.2 meter offset to those distances. What you want is that, and that, and that, okay? So you're going to have to add or subtract 0.2 to the distances that you calculate off the figures to get the moment arms from A. That's what you're gonna have to do there, okay, on that one. All right, so for instance here, what I'm going to do here is let's find the force associated with that long narrow triangle. Well, excuse me, long narrow rectangle. That thing is 210 newtons per meter high. So that's the weight you would accumulate, or whatever that load is, per meter. The length of it is 1.2 meters. Okay, and you can calculate that out and get that force. That's 252 newtons. So that force there is 252 newtons. Okay. Now, what's going to happen here is you want to know what the moment arm is for that thing. Now, the moment arm for that is going to be 0.8 from point A. And the way you calculate that is you're going to take 1.2, and then that's a rectangle. You're going to divide that by 2. Okay, and that's 0.6 is what that is. And that is this dimension right here. That's from the edge of the rectangle on the right-hand side. But we're taking moments about A, which is 0.2 meters over from there. So you're going to have to add 0.2. And that's what 0.8 is. Half of 1.2 plus 0.2 meters more. That's how you get the distance from A. So this distance right down here is 0.8 meters. Okay. And that just has that little extra thing in there where you've got these different shapes, but where all those shapes intersect is not where we want to take moments about. We want to take moments about 0.2 meters further to the right. So we got to account for that. Okay. So you're going to run through that and get the information for all of these things. I would leave the large rectangle as is. You don't have to break it into a piece to the left of A and to the right of A. There's no reason to do that. Just calculate the force for the whole big rectangle. Okay. All right. And when you calculate these things, you're going to get some numbers, of course. And we're going to get the triangle is 318 newtons. So I'll just give you some numbers where you can check what you're doing. And that will be 0.6 meters from A. And then that big rectangle to the right, on the right-hand side, I guess I should say, that will be 814 newtons. And that will be, whatever it is 0.35. Yeah, I guess that's right. Okay. Okay. So what you're going to have then is you're going to have those three green forces, and you're going to know their distances now from A. So that's 318 newtons. And the one to the right is 814 newtons. And that's 0.6 meters. And this is 0.35 meters. Okay. So what you have now, you've taken that shape there, that distributed load with its three different pieces, broken each one down into a load, and gotten the distance that it is from A. And once you have that, of course, you can calculate the moment about A. Okay, and this is going to get a little messy here, but you know, I just never quite have enough space. So the sum of moments about A will be, what, 252 newtons times the 0.8 meters you're gonna have to, you're gonna have another thing to put in there, and then you're gonna have minus the 814 newtons times its moment arm, okay? And when you sum all that up, you're gonna get sum of MA, and that will come out to be actually negative 1314 Newton meters. And then you can go sum of Fy, and just run that, and what that's gonna come out to be, I screwed that moment up, my bad. Let's get that fixed. I busted that. I wrote down the force of the moment. That should be 107.5 positive, so that's 107.5. There we go. Newton meters, and that's going to come around counterclockwise. And then the force, that's the one that's 1384. So there's your answers right there. So I'm gonna need to see a few things from you on this. I want you to do the work. So do that one and that one. Get this distance figured out and that distance figured out, and get that stuff figured out and that stuff figured out. That's basically how you find that result. Okay. Doing all right with that? Okay. All right. So, I'll start grading that test. It usually takes me a weekend to grade through 30-some tests, so it'll be a little while, but I'll get them back to you. All right.